Hello, my name is Pratik Sane. I'm a graduate student at Electrical Engineering Department in San Jose State University. Today I'm here to discuss about the implementation of Altera Nios II subset architecture. This project was carried out under the guidance of Dr. Chang Chu. Let us start by looking at the Nios II overview. It is a soft IP core. It basically means that it is a microprocessor fully described in software that is usually an HDL such as Verilog or VHDL, and it can be synthesized in a programmable hardware such as an FPGA. It has a reduced instruction set architecture, that is, it has limited number of instructions unlike the x86 CISC architecture. It has a 5-stage pipeline. It may go up to 6, but usually it has a 5-stage pipeline. Then it has a 32-bit instruction set, data path, and an address space. 32-bit bus of the instruction set means that we can access almost up to 4 gigabytes of instruction memory. However, in our project, I have considered only 1 kilobyte of instruction memory and 4 kilobytes of data memory for simplification. There are 32 general purpose registers, of which a few purposes. We will discuss those shortly. There are 32 external interrupt sources. There is access to memories and peripherals. There's a separate unit for cache management, and Nios 2, since it is GA, it can use off-chip devices, off-chip peripherals attached to the FPGA as well. Then programming of Nios 2 is usually done in C++ using an Eclipse IDE, the standard IDE for programming Nios 2. Now let us look at the uh, overall architecture of the Nios 2. This is the fetch block. This is the decode block. This is the execute. This is the memory block, and finally this is the write back. So this is a 5-stage pipelining. In the fetch block, we have an instruction memory, program counter, and an adder. The adder adds 4 to the current program counter to increment the program counter to the point towards the next memory location. Then the program counter is simply a counter which keeps a track of where is my current instruction, and it simply points to the instruction memory, and the instruction memory contains all the instructions. Then this is the execute stage. This is the most important stage in the processor designing. In this we have a register file. It is a 32-bit 32 registers we have over here. It has 2 read ports and 1 write port. There are few registers in Nios 2 such as register R0, which is always hardwired to 0, and register R1, which should never be used by user programs and is used only by the assembler. Similarly, we have R29 as the stack pointer and R31 as the return address for the subroutine calls. Then we have a sign extend unit, which converts a 16-bit offset of the immediate data to the 32-bit field. Then we have a control unit. The control unit controls the whole processor designing. It sends out various signals such as branch, memory read, memory write, ALU control, and register write. All these control signals are passed on to the next stages, and depending on that, further action is taken. Then we have this execute stage. In this execute stage, we have the ALU. The ALU simply adds, multiplies, or does the logical operations depending on the ALU from the control unit from the previous stage. Now we have this adder block. This adder block is typically for branch and jump instructions. Usually all the instructions in Nios 2 are word aligned. That's why we shift left the instructions by 2 places, so that we can add the offset to the current program counter and the operation may resume from the branched execution. Then this is the memory stage. In the memory stage, we have the data memory. The data memory has one write port and one read port. These two memories are out of our design. That's why in my design I've initialized them using the initial begin block in Verilog. And since they are outside my design, I don't need to synthesize them. Then this is the write back block. In the write back, simply the contents of the register which need to be written back are written back to the decode stage. Uh, and these signals are passed back to the decode stage, and the right data is given from the mux and the right address as well as the right enable. Right enable is not shown here, but it's usually there. Then we will look at the instruction types. In all the instruction types, usually the last 6 bits of the instruction field are reserved for the opcode. Then, depending on the instruction type, the remaining bits vary. This is for the I type, this is for the R type, and this is for the J type. In I type, it's usually the immediate value. That's why it's called I type. Then we have register A, register B. These are usually the addresses. Similarly, in uh, R type, there are register A, register B, register C. These all are the addresses which point to the register bank. They are usually 5 bits long to point to the 32-bit registers. In I type, the register B is the destination register, and the register A and the immediate value are the source operands. Similarly, in R type, register C is the destination register, and register RA and RB are usually the source operands. In R type, we have this extended opcode field. Since the opcode field is always to the value of 3A, the extended opcode field in R type decides the type of instructions. The uh, examples of these type of instructions are add, multiply, divide, etc. The examples of immediate type of instructions are add I, mult load, store, etc. Then we have these J type instructions. Examples of these type of instructions are call, which call the subroutine from the code. There's a 26-bit unsigned immediate value. This 26-bit unsigned immediate value can represent up to 256 MB of instruction memory. That is, it can jump up to 256 megabytes of memory. Then let us look at the pipeline execution cycles, which all instructions usually take. Normal ALU instructions like add, compare take usually one cycle. Then multi-cycle custom instructions and combinatorial custom instructions also take one cycle. Then branch instructions usually take 2 cycles since the branch is taken from the execute stage, as we previously saw in this diagram. The branch is taken from this stage. So to predict a branch correctly, we need at least 2 cycles. So one over here and one over here. Then if the branch is predicted correctly and it is not taken, then we will require 1 cycle since there is no branch taken, so only 1 cycle to execute it. Then if a branch is mispredicted, then we will need 4 cycles since that time we will have to flush the pipelining. Also, instructions like return, call, all these instructions which are related to the subroutines, they all take 4 cycles since for these instructions we need to flush the pipelining totally. Now let us look at the simulation of the design. I'm using the GTK wave and I've compiled the design using Synopsys VCS. I'm just appending only the required signals. Now let us look at the signals independently. So as we can see, the address goes on incrementing, and at a particular time at the address 100, my data of 500 is written. This is the answer of the dot product uh, code. So this is correctly verified. Then for the factorial code, my final answer is in the register R2. That's why I will append these two signals right back to decode register address as well as the data. And then let me convert them to decimal. So these are all the stack values since my stack is initialized to 2000. So that many times the stack is getting uh, expanded and shrinked. So let me show you how the stack expands and shrinks. See, the stack has started to expand. It's from 1992, then 84, and so on. Then it's expanding, expanding, expanding till a point over here, and then it will again start to shrink back, like 36, 52, and so on. And in the end, it will get back to its original value, and then I will get the result in R2, which is 5040, which is 7 factorial. Hence, the functioning of the factorial is also verified. To conclude, all the instruction types, that is I, R, and J, were implemented in the subset. The design used a stalling approach to tackle data dependencies in the pipeline execution. For the stalling approach, I simply compared the uh, current read addresses and the write addresses in my future pipelinings, and if they were found there was a match found, then I stalled the pipelining. Then stalling increases overall execution time of any instruction with hazards, but sometimes it's preferred in against forwarding because forwarding takes some additional hardware, and the stalling is cheap in terms of gate count. That's all. Thank you.